record this. Great for people online, and I should probably record for them like problem 16 off the homework. I've been explaining every hour. People seem stumped somehow. Oh, there's the bell. Yay. I should learn to not record till that second bell starts. Anyway, let's do our triangles separate. Let's have some strategy to our physics problems. It will somewhat do what I want. Oh, okay. Okay, make sure you write down the story about the penguin, and then we'll scroll down as we go, and it will not zoom in. I'm learning technology. Watch them, after I spent all this time and effort learning this technology, watch them take it away or change it next year. Anyway, we're being pulled by 10 newtons this time. You can draw penguins if you want. It encourages me to be lenient, taking away points. It does not get you extra points. Let's see. Okay, so we are definitely going to need components of this. If it's 10, our y component should be 6 newton, and our x component should be 8 newtons. Make sure you can calculate that for any number. I probably am still so nice, I'm going to use 3, 4, 5s on the test. Just because, although your actual staircases that we'll explore some more in later chapters, your actual staircases are 30 degrees standard. So we might want to know that one too. Okay. So, then let's free body diagram our penguin. Because this is your first physics class ever, you're allowed to then use the components, right? If I give you stuff at an angle, or if you're on the incline, do the mg sine theta and mg cosine theta and just write those separately. Don't confuse yourself with too many triangles. Okay, but this time we have to have it. We have to have our 8 newtons this way to the right. We have some force of friction back. So now we have a mu that's not 0, it's 0.5. So we have a force of friction is mu times the normal force. We definitely have gravity, which is going to be 20 newtons, 2 kilograms times 10 for gravity. Oh, but how much is that normal force? Is it also 20? It's Friday. Okay, you're at least suspicious enough to stay quiet. It's not 20. Okay. Oh, you still need the top? No. Okay, good. You can tell my explaining a problem has just devolved into listing the the important information. I got in big trouble with my Algebra 1 class because I've done this for 20 years. I look at a storing problem and my brain just picks out those informations. I don't even read the whole thing. I don't have a strategy for setting up my problem. I just list everything and my brain just picks it up. I train myself to do it. I have to do that. Come on. There we go. Okay. Since we went to all the trouble with our vectors over there, we can't forget. Okay, we have a 6 newton component over here. So if I put 20 newtons for normal force, it's going to yank the penguin off the ground. And if you actually try this, pulling 10 newtons, we could get a little scale out and pull 10 newtons on a 2 kilogram penguin or bowling ball or whatever. That doesn't work. You're going to end up with just 14. Okay, can you see why? 20 down and 6 up plus 14 up, and it moves horizontally. We don't pull our penguins off the ice. They like it there. Sorry. Okay, and this is the same. The floor only supports you as much as it has to. The bathroom scale. If you're still making this mistake, go home and do it. Put the bathroom scale by the countertop. Lean on the countertop with your feet still touching the scale. You can reduce your weight to like half or less. Okay. Okay, fantastic. The important part is that the friction only depends on the actual normal force. So you have to remember to subtract. 20 minus 6 is my normal force is 14. So my force of friction is 0.5. That's mu. times 14, that was my normal force, equals 7 newtons. And if I was really clever, because it's this arrow, I would say minus 7 newtons, where I have plus 8. Okay? So if I'm dragging something, and I might go easy on you on the test, I might have it not at an angle. I might just tell you, okay, it's 8 newtons forward, or maybe 10. And then I would have the full normal force. I wouldn't have to subtract. Could you do it both ways? We'll find out on the test review and the practice. 0.5 is mu. This guy, didn't I put up there? That's just a number. Very good. Where did I get 0.5 from? Come on, everything. With mu 0.5, I mean, in a text I would say, or on the test, the coefficient of friction is 0.500. That means 50%, or exactly half, of the normal force, literally the pressure between the penguin and the surface, or the object and the surface, gets converted into friction force. Okay, so it's like if I push my hands together in this example, I have half the grip that I'm pushing together will resist me sliding the hands across. Okay, you can think of it as a conversion rate of 50%. That's fine. That's what it is. Okay, so we want our acceleration, right? We want to know what happens. Because maybe it's 0. Calculate AX. Exactly. Oh, it deleted. I extend the page to do that, and it went to the bottom. Okay. So AX equals plus 8 newtons for the horizontal component of the tension, minus 7 newtons for the force of friction, divided by 2 kilograms. I don't know why that one had decimals. So we should get plus 0.50 meters per second squared. Sure.
Does that mean that the V0 was unnecessary? Because that was one of the...
It sure was. Well, in a problem like this, it was unnecessary. However, if it's a question of how much friction is going to be, is there actually going to be more friction than there is applied force in the horizontal direction? It could be decelerating. And a really smart student like Calvin would say, well, if it's at rest and I have more friction than applied force, then it shouldn't move at all. It won't even accelerate. It doesn't start. Calvin. So if I really want a legitimate question about does the penguin speed up or slow down being pulled in this situation, I have to give him some sort of velocity or speed to start with. Okay? So it's not relevant to solving the problem, but it's relevant to having a realistic problem. Does that make sense? Okay. Let's cut that.